It's a great honor for me to be invited to speak during this webinar conference. I wish I could be personally present over there, but anyway, this is the best that we can do. So I'm going to make a presentation on a topic which has been of interest to me for quite some time. This refers to exact inference in a multinomial distribution. This is in the name of Professor C.R. Rao, whose birth centenary was celebrated worldwide, is being celebrated worldwide for the last 3-4 months. This is my joint work with Professor Monisha Pal of Calcutta University Department of Statistics and Madam Papia Sultana of Department of Statistics, Rajshahi University, Bangladesh. The abstract says we have a 4-cell multinomial distribution specified by the 3 parameters P, Q, R. So the 4-cell probabilities are P square, Q square, R square, and the last one is 2 times PQ plus PR plus QR. So that the total is P plus Q plus R whole square, and the parameter space takes care of P plus Q plus R equal to 1, strictly between 0 to 1. Now the question is, there are 3 parameters PQ are bounded by the linear relation. So if we are talking about unbiased estimation of these parameters, and if we can take care of 2 of them, the third will be automatically understood because of this linear relation. So essentially, we take the problem of unbiased estimation of P or Q or R one at a time, and question number 2, simultaneous unbiased estimation of P and Q and hence of R. So these 2 issues are separate, and there is a difficulty level attached to the second problem. The first one is well known. I would assume that the listeners, they are already familiar with the question of unbiased estimation of P when we have P squared in the model as one of the cell probabilities. But getting simultaneously estimates of both P and Q, that's a bit tricky. And we know that no finite sample size strategy will suffice for these unbiased estimation problems in the exact sense. So we are talking about unbiasedness in the exact sense. So I'll be dealing only with simultaneous estimation of P and Q. That is what is essentially mentioned in this page as well. So we are looking to the problem. So we go for a sequential sampling strategy. So we collapse the cells 3 and 4. These are the cells R square and 2 into PQ plus PR plus QR. These 2 things we club together, and that total we call theta 0, and P square we write theta 1, and Q square we write theta 2. So essentially we convert the 4-cell category into a 3-cell category, theta 1, theta 2, and theta 0. And our parameters of interest are P equal to square root of theta 1 and Q equal to square root of theta 2, while theta 1 plus theta 2 plus theta 0 is equal to 1. So we now proceed to define a 3-way sequential sampling strategy in order to unbiasedly estimate P and Q simultaneously. So it says we continue sampling the units from the multinomial defined by the categories 0, 1, and 2. Let us recall 0 defines the category with probability theta 0, 1 is with theta 1, and 2 is with theta 2. So these are the 3 categories, and we continue sampling until all the categories are represented. That means until each category is represented at least once. So that is our sampling strategy, sequential sampling strategy. This amounts to stopping when the frequencies in the 3 categories are of the forms we have displayed it here. So there are 3 types of frequencies: frequency type 1, frequency type 2, frequency type 3, because we want every category to be represented. So these three types tell which one is the last category to show up. So frequency type 1 shows that category 1 is the last to show up, and before that, prior to that, we already have 2 and 0, K1 and R1 times, both greater than equal to 1. So they both have already shown up, and category 1 is the last to show up. That is the type of frequency 1. Frequency type 2, when category 2 is the last to show up, and frequency type 3, when category 0 is the last to show up. So this is my sequential sampling strategy, where we continue sampling until every category is represented at least once, and these three are mutually exclusive and exhaustive, collectively exhaustive sampling strategies. Frequency type 1 amounts to observing one unit of category 1 at the end, after having observed units of the other two categories, at least one of each category. Likewise for the other two types. These are, as I said, these are mutually exclusive and collectively exhaustive sampling strategies. We can verify that in terms of getting into frequency type 1, the termination via frequency type 1, that is P1, P2 and P3, those have been displayed here. And further one can verify easily that sum of the probabilities is 1 as it should be. So these are collectively exhaustive and mutually exclusive frequency types 1, 2, and 3. So given a sample which is a frequency count in one of these three types of frequencies, we have to find a method for estimation of P and Q unbiasedly. There are several remarks here. If we look at samples of type 1, which says that 1 is coming at the end, so before 1 we are getting 2 and 0, let K be the frequency of 2 and R be the frequency of 0 before the type 1, before category 1 shows up. And or it could be 0, R, 2, K, 1. So amount to observing category 1 at the end. So what is interesting is that 1 is coming at the end, and before that we have both 2 and 0 showing up either way. Similarly, we have 2 at the end, or similarly we have 0 at the end. So this suggests observing which category you are observing at the end, that is described by this kind of description of the frequency counts in the three categories. Remark 2 says 2K, 0R, 1 has to be interpreted as comprising of all possible combinations of K plus R units in the two categories 2 and 0, with frequency counts as specified by K and R. Likewise for the other two types. We have more remarks coming up. To unbiasedly estimate P, which is square root of theta 1, this is the representation that is used classically. Theta 1 times theta 1 to the power negative half, which is theta 1 times 1 minus theta 2 plus theta 0 whole to the power negative half. Now you go for infinite series expansion, the usual expansion of this thing, and it leads to summation j greater than equal to 0, a suffix j, theta 2 plus theta 0 whole to the power j times theta 1, where a suffix j is this quantity. This is a standard representation for j equal to 0, 1, 2, etc. So the above expression suggests that there are probability expressions of 4 different types. Everywhere we have theta 1 as a common factor. So category 1 shows up in the very first draw. That probability is theta 1, because essentially we are sampling from theta 1, theta 2, theta 0 trinomial population. So category 1 shows up in the very first draw. That probability is theta 1, and this corresponds to j equal to 0. For j equal to 0, aj will be equal to 1 and the coefficient will be theta 1. That is exactly what is happening if we find category 1 showing up in the very first draw. Then successive units representing the categories 2, 1 or 0, 1. For j equal to 1, we are getting either 2 followed by 1 or 0 followed by 1. Similarly, for j equal to 2, we get 2, 2, 1 or 2, 0, 1 or 0, 2, 1 or 0, 0, 1. That is how the whole thing is going on. That is how we can see the role played by j. It is like waiting time. You wait until you get the category 1. That is represented by theta 1. And when you are waiting, you are getting all possible combinations of the categories 2 and 0. Classification of samples as per the description of the sequential sampling strategy. We have non-terminating sample. For j equal to 0, if the very first unit is category 1, then that corresponds to j equal to 0. That is a non-terminating sample, because the sampling will terminate when all the categories have been represented, each one at least once, with a frequency of at least once. So theta 1 coming up right in the very beginning, which corresponds to j equal to 0, that is a non-terminating sample. Similarly, for j equal to 1, we have 2 followed by 1 or 0 followed by 1. It is still non-terminating, because to terminate, we have to have all the 3 categories represented. Look at j equal to 2. So there are 2 units before hitting the category 1. So those 2 could be 2, 0 followed by 1 or 0, 2 followed by 1 or 2, 2 followed by 1 or 0, 0 followed by 1. In case of 2, 0, 1 or 0, 2, 1, all the 3 have been represented. Therefore, it is a terminating sample. On the other hand, 2, 2, 1 or 0, 0, 1, they correspond to j equal to 2, because I am getting 1 at the third attempt, but still they are non-terminating, because for 2, 2, 1, 0 has not shown up yet, and for 0, 0, 1, 2 has not shown up yet. So we have a classification of the samples corresponding to different values of j, 0, 1, 2, ... And the classification corresponds to whether the sample is a terminating sample or non-terminating sample. In our description of the estimate of P, we have to base it only on terminating samples. When the sample terminates, when sampling terminates, we have the entire sample, the entire body of data, so we propose an estimate of P. That is what we do normally. So in our description of P hat, we have to base it only on terminating samples. Note that in the expression for P, for each j greater than or equal to 1, the extreme terms corresponding to 2j1 or 0j1 are non-terminating samples. For j equal to 3, before hitting the category 1, we have 3 observations prior to that. Those 3 could be combination of 2 and 0. It could be exclusively 2, 2, 2, 2 followed by 1, or 0, 0, 0 followed by 1. This is what I am referring to here as non-terminating samples. Other than these 2 extremes, all other combinations of 2 and 0 for a total of 3, 2, 2, 0, 2, 0, 2, 0, 2, 2, 0, 0, 2, all kinds of combinations of 2 and 0, those are terminating samples. That is what is meant here. In the expression for P, for every j, the extreme terms corresponding to 2j1 and 0j1 are non-terminating samples, while all the rest are terminating samples belonging to frequency type 1, because 1 is showing up at the end. The non-terminating samples will denote henceforth by initial units with a semicolon ... because we still don't know what else is coming up, where the rest comprise of all possible descriptions until it terminates in one of the frequency types. So formation of P hat based on terminating samples. Here I am giving a description of P hat based on terminating samples. The whole idea is coming from the expansion that we have for P, which is square root of theta 1. This is the leading slide where we are showing what is P, how P has been expressed as a function of all these thetas. This is the basic idea. So for a sample of the type, we already mentioned that for j equal to 0, the unique number 1 is a non-terminating sample and A0 equal to 1. Now we are talking about sample of size 201 or 021. These are terminating samples. Sample size 3. We already have all the 3 showing here. So IS, that corresponds to A2. A2, if we expand, A2 is half. So the indicator of the sample is half. What does that mean? That means in case I get 201 or 021, I will terminate and I will use the indicator half, and I will develop a auxiliary randomization through use of a Bernoulli trial with success probability half, and I will execute it. If I get success, my indicator value will be 1. If I get failure, my indicator value will be 0. So my p hat will be 1 or 0 according as I get the result of success or failure by performing an auxiliary non-randomization, a Bernoulli trial, with success probability indicated by this indicator function IS. Similarly, if I am talking about j equal to 3, then there are 3 prior to getting 1, and all these 6 descriptions here, 220 followed by 1, 202 followed by 1, etc. All the 6, they refer to terminating samples with j equal to 3. A3 is 3 over 8. So the indicator for any of these samples is going to be 3 over 8. So I use the auxiliary randomization Bernoulli trial with success probability 3 over 8, and I act accordingly. If it is success, I say p hat equal to 1, otherwise I say p hat equal to 0. Like that, even in general terms, when there are k plus r observations before I hit to the category 1, and if both k and r are strictly positive, then I get AJ for every sample S. Here 2k and O are referred to all possible 2 to the power j terms, excluding the 2 extremes, because the 2 extremes, 2 are 2j1 or 0j1, they correspond to non-terminating samples. So, but for those 2, for all others, we know we can use AJ. Here IS is the usual indicator function, as I mentioned, with a designated multiplier for every such sample S. And this refers to what is known in the literature as auxiliary non-randomization. So my sample starting with 1, indicator is 1. My sample of size 2, starting with 2 followed by 1, or starting with 0 followed by 1, it is j equal to 1 and aj equal to half. Therefore, my indicator is half for every sample of this type. Next, my indicator is 3 over 8 for every sample of the type 221, 001, 201, 021. So 2j1, that is what I was mentioning, a series of 2 followed by 1. That is an incomplete sample, non-terminating sample. That's why I use semicolon ... Similarly, I have all zeros followed by 1. That is also an incomplete or non-terminating sample. But my indicator function is AJ, depending on how many J's have shown up before. So I is the usual indicator function. It must be noted that the non-terminating samples of the type 2k1 or 0k1, they do terminate with probability 1, conditional on the first part. I have got a bunch of 2's followed by 1. If I continue, because I got 1 for the first time, I stop here to provide my estimator. But if I continue, then with probability 1, I am going to stop somewhere. That is what it says. Every non-terminating sample will terminate with probability 1, conditional on the first part. The idea is to identify the nature of the complete sample by referring to the first part which has been observed and then assigning an indicator to it. That is exactly what we are doing. We are looking at the sample, whether it is terminating or non-terminating. We first hit the category 1 because we are primarily interested in estimation of P, which is called root of theta 1. We are developing the whole thing keeping theta 1 in mind, which corresponds to category 1. Therefore, my sampling I will stop the moment I get 1 for the first time. it may be a terminating sample or a non-terminating sample. And even if it is non-terminating, I know if I would have continued, then I would get, it would terminate with probability 1. So the idea is I identify the nature of the complete sample just by referring to the first part, because first part helps me in providing an estimate of P based on whatever I have observed so far, that number K. That gives me a K and all that. Let's take up some example. For unbiased estimation of Q, we reverse the roles of the categories 1 and 2 in the multinomial setup. There is no need to change the category 0. So samples of the type 2 dot dot dot, 1 2 dot dot dot, 0 2 dot dot dot, etc. Even though these are non-terminating samples, now for estimation of Q, my emphasis is on category 2. Therefore, I stop the moment I get 2. And accordingly, I allow my estimator to be constructed depending on the value of J, the number of ones and zeros preceding first appearance of category 2. So we can skip the details now. So now I take up some illustrative examples. So this one talks about the case when we are observing the units one by one through the trials. The first trial results in an observation from category 2. Next one again from category 2. Next it comes from category 0, followed by 0, followed by 2, followed by a succession of 3 zeros. And finally at the 9th trial, we get category 1 and we stop. Because our idea was to get hold of category 1 for the first time, so we stop here. And we find our head count J equal to 8, and therefore my computation tells A sub 8 equal to 0.1964, and therefore for this particular sample, the Bernoulli trial will have the success probability 0.1964. We execute the trial and we find that it is a failure, and hence P hat equal to 0. Again, from the same sample, Q hat equal to 1, because category 2 is observed in the very first unit in trial number 1. We can avoid such indicator-based estimates by repeating the exercise independently some n times and taking the average score. So this last part we explain with reference to estimation of P. So I'm talking about 20 repetitions of the trial. The serial number 1, the nature of sample, it is terminating, J equal to 12. That means after a series of observations up to 12 runs, covering both the two categories 2 and 0, at the 13th trial, we find the category 1. Therefore, it is a terminating sample. A sub J, A sub 12 is given by this math, and we perform a Bernoulli trial with success probability A sub J, and we end up naturally, it seems that we have ended up with a failure, so P hat is 0. The next observation coming from another independent sample is also terminating in nature, J equal to 15. So at the 16th trial, we got hold of the category number 1. This is my AJ. This again results in P hat equal to 0. There is a non-terminating sample, J equal to 0. That means right at the first attempt, we got the category number 1. Therefore, A sub 0 is equal to 1, and this time P hat equal to 1. So it goes on like that. We have got a bunch of terminating samples here. Only one is non-terminating in this first lot, and in the second lot, we have got 2 more non-terminating samples. But whatever be the case, we know the interpretation for J, computation of AJ, and carrying out the corresponding Bernoulli trial with success probability AJ and getting hold of the score 0 or 1. So eventually we find that there is 1, 2, 3, 4, 5, 6. There are 6 ones. Therefore, my average over all the 20, that leads to 6 over 20, which is 30%. Surprisingly, in this, it is quite surprising that in this particular simulation, we started with P equal to 0.3, Q equal to 0.5, and R equal to 0.2, so it is remarkably identical to the true value that was taken for carrying out this simulation. But anyway, that's accidental. Let me now talk about simultaneous unbiased estimation of P and Q. As I said before, in this particular illustrative example, that once I have P hat equal to 0, that comes out of the Bernoulli trial consideration. But in this example, Q hat equal to 1, because the very first trial resulted in the category number 2. That's why Q hat equal to 1. But for simultaneous estimation of P and Q, unbiased estimation, let us start with this remark, that unbiased estimates for P and Q are based on the indicator functions, which are basically AJ values depending on the desired outputs. But this time we need two indicator functions, one referring to P and the other referring to Q, even though they are both based on AJ values. So for P hat, we identify appearance of category 1 for the first time in the sample. And while for Q hat, we identify appearance of category 2 for the first time in the sample. Note that these AJs, they form a, it's interesting to note, A0 equal to 1, A1 equal to half, A2 equal to 3 over 8, and so on. They are decreasing sequence, and not only that, any two of them together, AJ plus AK, is strictly less than 1. That's something very interesting to note, and that is what is being utilized quite profitably in this context. So for P hat, we identify appearance of the category 1. So that means there is a score J, which means the number of 2's and 0's preceding the appearance of category 1. And we use K for the number of appearances of 1 and 0 preceding the first time appearance of category 2. So we have got the notation J identified for category 1 and the notation K identified for category 2. Having done that, we find that we can compute AJ and AK from the given sample, and that AJ plus AK is strictly less than 1. Therefore, given a sample, whether it is terminating or non-terminating, we identify J for category 1 and K for category 2. Because this total is less than 1, we can perform a trinomial trial. Earlier we were doing Bernoulli in case of single parameter. Now because I have got two parameters P and Q, they have to be estimated simultaneously. We think of a trinomial trial with probability AJ, AK, and 1 minus AJ minus AK. AJ refers to category 1, AK refers to category 2, and the last component refers to category 0. Therefore, if we perform a trinomial trial with these probabilities for any given sample, looking at category 1, I identify J and hence AJ, and looking at category 2, I identify K and hence compute AK. So I have this trinomial trial with all the components known, AJ, AK, and 1 minus AJ minus AK. And therefore, I will end up with one of the three outputs, 1, 0, 0, 0, 1, 0, or 0, 0, 1, with an obvious interpretation. Now, if we consider and continue this exercise for a sample of size n, 20 or 30 or 40, averaging over such outputs would result in proper estimates avoiding the boundary value. If I look at single observation, it is 1 or 0 for every category. Therefore, these are the boundary values. These are not impressive. But if we take a sample of 20 or 30 observations together and take their average, then the resulting values will be proper estimates, as it happened in case of the earlier exercise that we took up here. Just for estimation of P, there were 20 observations. So the same exercise you could carry out for this particular data set by looking at P and Q simultaneously, and that would result in, for every sample, we would identify J and K and compute AJ, AK, and 1 minus AJ minus AK, and then perform the trinomial trial, end up with one of these three results, 1, 0, 0, 0, 1, 0, 0, 0, 1, with obvious interpretation, and then averaging over all those observations, all those sample outputs for a sample of size n, we would come up with P hat, Q hat, and hence R hat automatically by default in a proper way. and that would avoid the boundary values and we would get the estimates. So that last part, we are working on a small example now. I think that's it for the time being. Thanks for your patience and attention.
Thank you, Professor Sinha. Bapat is Professor Bapat.
Yeah.
Okay. Now it is unmute. Okay. Earlier it was muted.
No, now I want to. So are there any questions? Okay.
Maybe before any question comes, let me supplement.
Yes.
So towards the end, I talked about the joint estimation of P and Q and the simulation results. Now we have the results for 20 trials, for 100 trials, and for 1,000 trials. So with reference to 100 trials, again by taking P equal to 0.3, Q equal to 0.5, and R equal to 0.2, we find that P hat is around 0.3 and Q hat is around 0.55. So that is what we find in respect of the simulation carried out for 100 trials, and the standard errors are of the order of 0.08, 0.09, like that. So results are quite encouraging. That's the supplement that I wanted to mention.
Part of this work has it appeared somewhere, or you are going to? Has some part appeared?